I just need you every Tuesday. That's okay. Yeah, show you some. Oh. Yep.
You run it out and the problems are really flood.
Hey everyone, welcome back. We'll start off today with reviewing the exam. I'm happy to take any questions you have about the questions. Organizational, we covered most of it on Tuesday. Just remember tomorrow is the deadline for announcing your projects, and then next Thursday there will be a guest lecture with mandatory attendance, and there will not be a class on Tuesday. Okay. So, the question here was to style like a set of HTML according to those rules. And so, what are the three rules here? What is the special thing about the first rule? Yes, it's a child. It means like a direct child, right? Not a descendant operator. And so that means that wherever a B is directly nested in a P will be underlined. This one here? Any child? Any descendant, yes. That will be like stroke out. And then this class definition here is fairly simple, right? And so for this text piece here, I have like added the underline and the strikeouts. So you see the first case, the PB occurs twice in the first paragraph here, like this consecutor adis piecing, whatever. And then an acceptor sind okayet. And then we have the div B with the line through happening here. You see here we start a div, and then we have nested a B, but it's not directly in the P, so the underline doesn't apply because it's within the span. Well, actually, the underline here would apply, but it's overridden by this one here. I don't think that the text can be underlined and stroked through at the same time. So here the order matters. And then finally we have the class definition. Yeah.
Wait, one more question. I also thought that if you're selecting a child that was more specific than if you selected it.
You're right, but this is actually what's rendered in the. Okay. Let's look it up. If I find my cursor. So I got this wrong actually in my example here. This is, no, it's stroked through but not underlined. Let me see. Yeah, so this is P, diff B, any child, line through PB, text array curation underline. And then here we have the PB within a span, and then this here should be both underlined and stroked through, but is not, in fact, because of the order. So like this is just how it's actually output. So if anybody got that wrong, do you guys remember who graded this one? So if we'll review this, if there is an ambiguity with what we said on this, then we'll kind of fix that. Well, anyways, CSS can be tricky as we see. So the second question was about source code, document object model, and scalable vector graphics. Question was, what is the relationship between what is shown in the elements window of the inspector and the source code you require to implement in the assignment? So can anybody explain that? How is the source code influencing what you see in the element window? Yeah.
Source code is usually like the first thing that inflates the elements window, and then you get it inflated over time.
It's one way, that's definitely possible. Essentially, think of the source code being the stuff that generates whatever is in the element window, right? The element window can be identical to the source code if it's just simple HTML markup, but if the source code contains both HTML and JavaScript, you will likely dynamically manipulate the DOM, and then you will see whatever you've done in JavaScript to the DOM in the elements window. And so that's the relationship here. And then this question here, what is the document object model and what is it used for and how is it done?
The DOM is like the browser's internal representation.
Exactly. So the browser is the internal representation of the elements, but it's also an API for us to interface with. So it's both. We have the DOM API and we have the internal representation. The third question, the third part is what is SVG? And SVG is quite obvious. SVG is scalable vector graphics. And what is the relationship to the DOM? So SVG is part of the DOM, right? It's just like it's text like HTML is a different, like slightly different syntax, but it is simply part of the DOM. So here are our reference answers. SVG elements are part of the DOM, hence they can be programmatically manipulated just like HTML elements. Who found this one tricky? Okay, so the question here was really to first understand what this code does at two different time points. So here, this what you see up there is the SVG as it is specified in up here in this piece. So we have three rectangles, one with a height of 40, one with a height of 120, and then one with a height of 20. With a y position, height of 10, 120, and 120. So then we do some data-driven manipulation, but the trick here is that we have two different time steps with two different data sets that we pass in. So we pass in first a data set of 300, 200, then we wait until we hit time point 2, and then we set another data set. And so what will happen after I execute this for the first time? So what happens here is that we have an enter append rectangle, and then we have a styling on the selection. If we have a SVG select all rectangle, then here we explicitly append a rectangle, and then here we style our selection, our initial selection. Yeah.
So two rectangles will change according to the new specification, but this one will remain the same.
Okay, that's correct. So here we see the result at time 1. So we have two bars that are correctly updated, one bar that wasn't correctly updated. The order here matters. The first two rectangles will be updated. The third one, which is the skinny one, that will remain as it was initially. And then at time point 2, we add 4 elements in here. What will happen? Which piece of code is relevant for that? Yeah, the enter. So we have 3 SVG elements, so those 3 will be styled as I would expect. But then here we will have, for the 4th element, we will have the enter selection, and that simply gives us a square that is white. And so this is what this looks like at time point 2. And how do I fix those two things? What is missing? An exit and a merge. And so to fix that, you simply have selection.exit.remove, and then selection enter underscore selection.merge. Any questions about this? Okay. Question was, why is interaction important in visualization?
Allowing the user to touch the data increases their memory of it long term.
Yeah, touching and manipulating is understanding. That's one piece of it.
Many times you cannot represent all the data in a single resource.
Exactly. So those are the two main reasons for interaction: being able to explore data, data that is too big or too complex to show at once. Also, interaction amplifies cognition. If you can touch things, we can observe cause and effect. The second part of this question was about these different taxonomical terms. Data and view specification was our higher level category, and you were supposed to explain and give examples for visualize, filter, sort, and derive. And so visualize is choosing the visual encoding, for example, selecting a bar chart in Excel, selecting a bar chart for a table visualization in Excel. Filtering is removing items to focus on relevant items. For example, as we had in the Home Finder, filter only homes that you can afford. Sorting is exposing items according to patterns or sorting criteria. For example, sorting homes by price. And deriving is derive values or models from source data. And a simple example here would be a log transformation that I apply to my data set. Yeah?
Which paper did this
that came from the interactive dynamics from Herr and Schneiderman. The second mandatory reading we had. Any questions? Great, so then we had the question on design. When drawing bar charts or line charts, should scales always start at 0? Why and why not?
So like, no, because sometimes you can't see trends. Like if you have values that are up around 50 and you want to see the trends in that data, if you use something that goes from 0 to 60, you're not going to be able to see.
Yes, exactly. And the other reason why sometimes it's difficult?
0 may have no meaning with your data set.
Exactly. So temperature is a good example where 0 isn't really particularly important. And so yes, these are two good reasons. However, you have to be also careful about not deceiving people, right? You have to be very explicit about that. And so our reference answer here was scales don't necessarily have to start at 0. Some data sets don't have a meaningful 0 point, and some effects can't be shown properly when scaling everything to include 0. And then describe at least 3 guidelines for faithfully representing data. I put up 5 here. Use a baseline that shows the data, not the 0 point. Frame the data appropriately. Don't cherry pick what to show. Show data variation, not design variation. Use the best visual channel for the most important aspect of your data. And the visualization should show all of the data and only the data. So if you mention 3 of those, you got full marks in this. Then we had the question on marks and channels, and I'm going to go fast here because I'm assuming that everybody understands this. Here it was about listing and ranking at least 3 magnitude and 2 identity channel, and the answer here is simple as chart, right? You could have picked any of those. If you put them in the right order and gave us enough examples, we were already quite happy. Then the question is, why are not all quantitative channels equally good? Name and describe the law that governs how useful a channel is for describing quantitative values. Anybody remember the law? Stephen's psychophysical power law, exactly. We didn't really care for the name, but what is the point of the law?
That like our perception is always linear, depending on like what channel is used.
Exactly. So the stimulus, the intensity of the stimulus does not always linearly correspond to what we perceive of the stimulus. The only one in Stephen's experiments where this relationship was linear was the perception of length. And so here's this chart where we had like brightness, depth, area, which we underestimate in our perception, and then saturation and electric shock, which we overestimate.
Why are you saying these are quantitative channels when there's no actual numbers associated?
It's physical intensity, like the physical intensity of the stimulus.
See, what's the units there?
It can be anything.
Channel.
It can be anything. It can be meters. It can be.
Relative units, right?
It's relative units, yeah. So, like the electric shock will have a different unit than weight, right? It's just magnitude of that. So no electric shock versus 1 unit off versus 2 units off. Yeah.
So imagine if you know like the response of these things, they could be useful, except for like maybe there's a large variance between people. Is there a chart that shows that sort of thing?
So these kind of fundamental perceptual principles are remarkably robust across populations of very different, let's say, ancestry. There's a lot of cultural variation when we talk about higher level things, like reading direction plays a role, colors. Some cultures don't have distinct colors for blue and green, and then there is experiments that those people actually cannot easily distinguish between blue and green if they're given like an association task. But these very fundamental perceptual things are very robust across all humanity.
So I can effectively encode things with electrical shock if I want. I just need to know that behavior.
Well, but you need to calibrate mentally for that, right? And it's like, it's not going to be easy for you to kind of map that. So I think that with a ton of training, you maybe can like mentally compensate for that. But the point here is that it's absolutely like it's easy for us and it's natural. It just is the way it is when we use length. but brightness we tend to underestimate, right? And if we know that, we can like mentally calibrate, but we can't make ourselves see it differently. Yeah.
I was thinking about how the light factor may affect this.
Oh, you mean like the person's physical condition and so on?
Yeah, I mean, to manipulate the data, to write this light factor.
Oh.
So, which is a quotient between.
Yeah, so the lie factor here is not really captured with that. The lie factor is about like essentially the magnitude of the of the object on the screen or on paper compared to the magnitude in the data, right? So there it's really about distortion or maybe wrongly using like diameter instead of area and so on. And so this is lower level, the lie factor that applies to these higher level encodings. Okay, yeah, this is our reference answer, but I think I've said everything here. And then this visualization. So this visualization shows the voting patterns and how similar those voting patterns are between senators. And I picked an outlier here to be our center. Our outlier here is Bernie Sanders. He's one of two independent senators. And I wanted to see, is this independent senator independent or more like other people of a party? And so what can we see in this chart? What are the marks used in this example? Let's start with that. So the marks are the points, the circles, exactly. And what are the channels used? Color, and what's this color encode? Party, and then we have the second one, distance, and that encodes the similarity, yes. So one big thing that you need to figure out in this chart is what does angular position mean? Nothing, yeah. So and that's a tricky bit here. Like, why do you think that somebody chose angular position here, or like a circle instead of just having like a line with dots?
To show all of them, was cleaner to show.
Exactly. So it gets kind of cluttered in here already, right? And so if I had all of those people like overplotting each other, that's probably the reasoning for them to do that. So what's your judgment? Are the marks and the channels appropriate for the data and the independent point of the visualization?
Like, to me, the fact that you're using circle, and I know that it's measured by radius, right? Radius from the center. But to me, it seems like one could very easily get confused between, like, when they're all there close in the middle, you know, they all look really close, and then you may have some that are in between, and it's hard to, like, gauge that, right? Like,
Yeah.
I think there's some sort of, like, misperception that can happen from having that.
Yeah, so like also what this visualization somehow conveys is that this guy here is very different from this guy, right? Even though it's not supposed to show that. But my judgment here would be it's pretty accurate for doing exactly the one thing, comparing other people to your person of interest. But for everything else, it's actually not necessarily the best visualization. But overall, I would not give this visualization a failing grade. It's not completely terrible. It's engaging, and you can play with it, and it doesn't contain any it's slightly misleading sometimes, but it's fairly accurate. And so I posted a link to an analysis of this chart and the redesign about it. For a 1D redesign, like a redesign that I would do here with this data would be simply to have like a 1D dot plot. That would be very simple redesign. Then the second question here is to also use a second dimension of political leaning. And so here is this redesign by Alberto Cairo, where you see like the similarity to, in this case it's McCain, similarity to McCain, and they're liberally conservative, and so suddenly you get a scatter plot, a 2D scatter plot. That's one possible redesign. Of course, there's others. Any other questions about the exam? So, second exam is going to be like similar in style to this one. There's going to be like a redesign question just like this one. There is not going to be coding questions on the second. Okay. So last time we stopped talking about tabular data. The one thing that I want you to take away here from this lecture today, there's two things, or actually a couple of things that I want you to really take away is that depending on the type of the table that you're trying to visualize, you need different visualization techniques. And these variations can be in terms of scale, the number of dimensions, or the number of records, but also in terms of homogeneity. And we had this exercise, remember, where we had like a completely homogeneous data set, where we had like people and heart rate of those people, like all of the cell values were of the same scale, of the same data type, compared to here, where we have a table where people are again the items, but then we have other attributes, including numerical and categorical, in the table. And so here are just like my estimates, and these are of course like approximate numbers. I can do about 50 dimensions with just visualization. If I have much more than that, I need analytical methods. I can do about 1,000 records with just visualization. If I need more than that, I need analytical methods. And of course that depends a lot on the heterogeneity of the data. And so this is kind of like this overview of these big techniques. And we actually didn't get to any of those techniques in detail yet. But we have like scatter plot matrices and parallel coordinates where you don't actually have to use much analytics on top of them, like no clustering or ordering or anything like that. For heat maps, they're very scalable for homogeneous data, but you usually need some kind of like seriation algorithm. That's usually, very often that a clustering algorithm is used for that, to reveal any patterns. And so the seriation algorithm makes those like orders that you can see here appear. And then on the extreme side, you have things like projection techniques, multidimensional scaling, principal component analysis, and then you take like a high-dimensional data set, find like what is the principal component, or like a two-dimensional representation of it, and then project this into 2D space. And so we'll be talking about those things in the rest of this lecture. And there will also be another lecture on clustering techniques and some other algorithms that we commonly use in visualization. So I'm gonna skip over those quite obvious things. And then we talked about tabular grid matrix representation, and then here I didn't have audio, and so I'll play this.
Information than previously possible. Recently, Ron and I have turned to the problem of dealing with large tables.
For example, this is a table of the 1986 baseball statistics with 323 rows of players and 23 columns of data. We can put the data into a spreadsheet, but even using a 21-inch workstation display, the data requires 9 full-screen vertical scrolls and 2 horizontal scrolls, making it hard to work with. It's hard to find players or see interesting patterns. In short, it's hard to make sense of the information. We've devised a new way of visualizing and interacting with large tables called the table lens, which exploits graphical representations to compress the information onto the display. In this column, at BATS, we integrate a familiar bar chart representation directly into the textual view of a table. Some of the rows, those in focus, show underlying textual values along with the graphical bars. Other rows, those in the context, show only graphical representations, thus requiring less space. By displaying the entire table graphically, with only some of it in focus, this 324 row by 24 column table can be shown using a portion of the screen. The table lens displays 30 to 100 times as much information as a spreadsheet in the same space. With a small set of manipulation operations, the table lens allows fluid navigation and exploration of the data. The focus area can be manipulated using control points and/or keyboard commands. The number of cells in the focal area can be increased or decreased. The focal area can be moved to different rows or columns. Since the essential geometry of the table is preserved, multiple focal areas can be created. To facilitate browsing of context cell values, a mouse feedback area at the bottom of the window shows column, row, and value information. The graphical representations make it easy to spot trends and patterns and to isolate outliers or unusual cases. For example, sorting a column can reveal relationships to other columns. Here, sorting career at-bats reveals correlations in several nearby columns. Notice that career hits is strongly correlated or proportional to at-bats. In other words, most players have similar batting averages. Some players stick out from the curve, two well-known batting stars, Wade Boggs and Don Mattingly. To confirm these observations, we divide career hits by career at-bats, creating a new column, career average. The batting average curve is reasonably flat, as the correlation of the curves suggested, though increasingly noisy with decreasing career at-bats. Furthermore, the length of the bar shows that Boggs and Mattingly have the highest two career averages. If we focus on the salary column, we see that Boggs and Mattingly are paid relatively well for their top-flight batting performances. Also note that salary is somewhat correlated with career at-bats. Team and position of a player categorize players into different groups. Category values are displayed using blips. In focus columns, the blip is colored and positioned in the cell according to underlying value. In context columns, since space may be tight, only color is used to indicate the value. Sorting on position separates the players by category. In other words, all light-colored and positioned blips are brought together.
So you see where this is going. So basically this works well for numerical and categorical data. Of course, labels are difficult to see in the zoomed out version. And then like here is like a current re-implementation of this in an extension, and I'll show this in a different context later again. This here is Bertie Fire, and Bertie Fire is a technique for creating presentations of tabular data. This is not meant for, like the previous use case for the table lens that was really exploring very large tables. Bertie Fire is for creating these graphical table summaries, and it's called Bertie Fire based on Jacques Bertin, the French cartographer that developed these like classifications of the visual channels initially. And he actually, like he lived before the computer age, he worked before the computer age essentially, and he created those matrices like in actual physical objects. And so he would create those like wooden sticks with data items on them, and then you could resort them mechanically. And so this French group has actually re-implemented basically his wooden his wooden matrix visualizations on a computer system, and I really like this.
When she moves her mouse on top of any tool icon, a tooltip appears at the top of the page to record its function. Tools are organized in groups. Clara first expands the MISC group and clicks on the H icon adjacent to the first row to mark it as a header row. She does the same for the left column. Then she expands the Shapes group in order to turn numeric values into shapes. She clicks on the circle icon next to the first row of the table in order to turn its values into black circles and squares. She is satisfied, so she presses the same icon on the next row and drags down until the last row. This instantly turns all table cells into circles and squares. Now Clara wants a more compact table. Each row can be resized independently using a slider placed next to it. Moving the slider to the right increases row height, while moving it to the left decreases it. She sets all rows to their minimum size by pressing on the topmost slider, drags down until the last row, then drags left to notify all selected sliders. She does the same for columns. She also zooms in using the provided functionality of the browser. Now she wants to tidy up the table. She drags over all black arrow icons, which immediately rearranges columns by visual similarity, which moves similar countries next to each other. She does the same for rows. Now indicators that are similar are close to each other. To better see similarities, she removes the grid by setting all white separators and black separators to their minimum value. Clara continues to format the table to exhibit more patterns and convey a clearer message. This includes inverting the values of a row, importance of a group page, to better show its correlation with another one. the household income. She also emphasizes two rows of a specific type by changing their visual encoding, increasing their height, and dragging them aside. She encodes women's suffrage year using lines, and household income using a bar chart. She can choose to reorder only a subset of the rows or to reorder all rows. Now she can already see country groups with Czech Republic in between that she moves away. Finally, Clara adds separators and annotations to emphasize groups.
So I think that this is really well designed, especially the interaction techniques, these like what's called cross sets, the way you manipulate those things across columns is really well done, and also the seriation algorithms that build in and so on. And so I really like this technique and would like to see that more. Like there's actually papers now, like visualization papers that use the tool, and you can actually upload your data set to this tool and do this yourself. We talked about this in some detail, and then it turns out that you can also combine, like the problem with many of those displays is that if I have heterogeneous data, I get a little bit into trouble. But if you're careful about, you can also make combinations thereof. And so here I'm actually showing a table that shows two completely different data sets. Like this, here's one data set, this other one is a data set. I don't want to go into the details here. And then on top of that, I'm showing even more context information. So I basically like have 4 or 5 different tables that are all that I can match up by a certain identifier, and that I simply place next to each other. And by careful labeling and color coding and choosing the visual representations, I can actually build a sensible table visualization for such a complex data set here. So now I'm going to talk a little bit more about this technique that we developed, and that's about ranking tabular data using these like item-centric visual encodings. So the idea here for this project was that rankings are super popular. So for example, if you apply to college, you might look at the ranking of a school. If you want to read a book, you might look at the New York Times bestseller list. If you want to see a movie, you might look at what is currently ranked at the top of the box office. And why do you think rankings are so popular?
Because we trust in other people's opinions.
We trust other people's opinions, yes, but then you could also use a score, right? We don't need a ranking. That's part of it.
Humans are better in comparison rather than assigning absolute score.
Yes, exactly. And so the problem with many things that we need to make judgments about is that data, like complex item or entities like a university, are really like hard to understand. There's so many facets to it, and so it's mentally demanding to really compare many of those different entities, be it universities or movies or whatever it is. And so that's why we like those rankings, because somebody has gone through this process and has said, well, these are the most important things for you to look at, right? But we've remember when we talked about what is a good movie, that is not an obvious thing to do. Like what is a good university and what is good for me is not necessarily not universally true, right? And so that's where this technique comes in. So we were trying to build a technique that at least, like we have these proxy data that mean something, and then we want to conclude something larger about this entity. And so right now, if you, for example, look at the university ranking, you will, like if you look at US News and Worlds, they have things like academic reputation, citations per faculty, student-faculty ratio, and then there's 0.4 is the value of academic reputation. 0.2 is the value of students per faculty. And then they have like one big formula and create this scoring. But that's of course like not in any way tailored to what you're interested in. Like are you a faculty member looking for a place to do research, or are you a student looking for a place to get a good education? Quite different questions. And so we built this tool to essentially try to make this a little bit more easier to do. And so here we have like a simple example of university rankings, and we have like an aggregated score. There's a little mistake here. We can also represent this score graphically here with a bar chart. So then this looks basically the same, but this one bar chart is a composition of multiple values. So we can support multiple attributes here. So we can say we have an attribute A, B, and C, and then our score is a function of A, B, and C. And in the simplest case, that can be like a weighted or a sum or a weighted sum. So where we have any weights, because I say, like for example, I'm a student, I care more about student-faculty ratio than I care about citations per faculty. I could say, hey, I have two different data sets that I want to have a maximum from, right? And I can come up with an arbitrary complex functions here. I can have products, nesting, or I can write an arbitrary complex function as whatever I like. And so we developed a visual representation for the weighted sum and the maximum. I'll only talk about the weighted sum today. There's some other details that I'll skip over here. So how does the weighted sum, the serial combiner, work? So we have here these like independent elements, and we can actually simply create a stacked bar chart by moving those over to each other. And then we can adjust the weights. For example, if we adjust the weight of A, then our visualization here would adopt. And in this case, we see that now, like the score, the overall score of Princeton is lower than of Cambridge and Oxford here at the bottom. And so we will have to update this ranking dynamically. So this is a video of the system. You see those different columns. We have faculty-student ratio, employer reputation, citations per faculty. I can resort these columns. I can sort the items by clicking on any of those columns. Now it's alphabetical. And then I create these combiner functions. And there I can basically create something like an Excel formula by drag and drop. Here I have this weighted sum. I can now sort by that. And then I can start playing with the different weights of these attributes that make up the score here. So by simply dragging and dropping and direct manipulation, I can adjust this ranking, and I say faculty-student ratio is more important to me, and you can observe that which kind of schools move up in the ranking accordingly. And of course, I can also decrease that, and you see absolute values at the top, so you can also put in absolute values if you'd like. So this technique assumes that a high value is good, which is not always true. Like for example, if you want to talk about p-values, like a low p-value is considered good. I don't want to get into the debate about cutoff for p-values, but conceivably low p-values are, everybody would agree with that, low p-values are better than high p-values. And so we kind of need a way to map like a value from its input range to a range where high means good. And so what we do is we basically have this transfer function, which is very similar to like the domains and scales that we discussed when we talked about the three scales. So we have a minimum and a maximum of data set, and we map this from 0 to 1. And here we have a linear mapping, so that means a value of let's say 30 here would correspond to a bar of about this height. We can create a simple inversion of that score, and so here now we have a value of 30 corresponds roughly to a height of 70% of the bar. So this is like a graphical way of expressing such a function. Since this it basically is a function representation, we can also say like use a more like functional representation for that, right? And so we can say y is a function of x, and we use this more like mathematical representation here. And one of our like co-authors thought this would be a great idea. and we actually did a small user study on this. And it turns out that out of the 9 people we asked, out of the 10 people we asked, 9 preferred the former one, and only 1 person preferred this one, and this person was a mathematician. We still provided both options, but in the end, it shows that this parallel alignment makes more sense to most people who are not extensively trained in interpreting this. So here we have scores for disciplines, like arts and humanities in this case. And this is this mapping editor. You see 2 histograms that show you an input range and an output range. Here, we're essentially adjusting this ranking, and this can be nonlinear transformations. You also see that there's a piece of code down there, and you can manipulate the code and can create an arbitrary complex function. And here you have this like different representation where the axes are orthogonal, and I can create these nonlinear functions. And so we also provide a couple of standard mappings. For example, we can invert here. And then if you invert arts and humanities, so bad, arts and humanities is good, then Virginia Polytech ends up at the top. Yeah.
What's this using JavaScript?
So this here is implemented in OpenGL, but I will show you like a JavaScript version of this in a second. We re-implemented this in JavaScript recently. So next question that you might want to ask, especially if you're a university administrator, is like, how can I like tune this ranking so that my university comes out best? And what are the different kinds of rankings for how I can achieve that? And so you can create multiple rankings and then compare them. And so what we do here is simply we place a couple of those side by side and then connect them with bump charts. So like in this first ranking, for example, Harvard would be at place 2, and it would be at place 4 in the second, and at place 1 in the third ranking. And these bump charts, they kind of like guide you through these positions across these different representations. And so here is this, again, a video of this where I can like independently manipulate those 2 rankings. So here I'm adjusting faculty-student ratio. You see the slope charts appearing, and then if I remove a column, for example, I have like a more massive change, and you can see that I have some schools that are now off-screen where we don't show any of those links anymore. So here is the JavaScript version of this, and that's kind of like built into the same tool that I showed earlier for tabular data visualization. So here I have, let me just clean this up a bit. So here, these are independent, like here we have universities, and these are independent independent columns. We have like the quality of education, we have the alumni, what is it? Employability, and so on. And so now I can sort by any of those values. I can sort by which are like the most highly employable alumni, and we see that there's a lot of schools here that have like a full score, the national reputation, what is it, national rank, and so on. So what I really want to do now is to create these combiner columns. And so here I will create a weighted sum column, and I will create this for, let's say, the quality and the alumni employability. And now I sort by that. Now I can dynamically adjust. Oh, I should be able to. Yeah, so here I can adjust the weights, and then we can see the updated ranking as we had it before. And so this is implemented in D3, and it works just as well as our OpenGL version. Okay. So next big topic is pixel-based displays. And pixel-based displays, I think it's quite intuitive what they do. Here, each cell is a pixel value and the pixel value encodes the cell value as color. And of course, as we have talked about a couple of times already, for these displays, order is critically important. So here you see an example, like an unordered heat map and an ordered heat map. And I can really see clusters here, and like a high cluster here and here, and low clusters here and here, which I can't really see in here. So this really relies a lot on like a sensible and usually like unsupervised learning-based ordering. And so if no ordering is inherent, then you use something like clustering. The thing is that those are very popular because they're super scalable. So I can like essentially plot one cell per pixel on your display. And if you use clustering, you can maybe even go beyond that because it doesn't matter if you lose a single row, the overall view will still look the same. And so they are great for homogeneous data. If I have large matrices that are numerical, then using something like that is ideal. Here's a comparison of like a grayscale heat map to a parallel coordinates plot, and you see the same kind of information, but it's much more compact representation if you use the heat map here. So this is kind of like a tangent. I might have shown this before. What is the pattern that you can see here? It's a question mark, and that's kind of easy to spot in a heat map, but it's not so easy to spot in a 3D bar chart. And so, obviously, if you have data like this, the usual rule, like use a bar chart if you can, does not apply. So you don't want to use the 3D bar chart. You need to use something different for that. And then here we have an example for heterogeneous data, and that's kind of like related to what I showed earlier. But the problem here is that these guys have encoded 5 different data sets with exactly the same colors. And I haven't been super careful about labeling either. And so that can be a little bit misleading and tricky. So you have like copy number, mutation, and gene expression encoded using the same color scale, but you have to be very attentive to pick that up. So I would say that this is not necessarily an amazing figure, but it's from a very popular paper. Of course, it's really about the data analysis in that case. And then remember that color mapping can be misleading. So we have the issue of colorblind users, where here you can't actually see this extreme outlier in like of these red cells here, and for a red-green colorblind users, this looks like there is actually no high value in here, so just be mindful about that, and don't use red-green color maps, use a red-blue color map if you create a heat map, or any other color combination. So these red-blues are quite common. So you can see that a problem like this, if you have red-green blindness, you can still spot that easily. And then I also showed this before, that color is relative, right? So those two values here with the star are exactly the same value. In one case, here, down here, it looks like it's actually high. Here it looks like it's low, but it also only depends on its surroundings. So all of these are these like perceptual principles that we talked about in the second lecture that apply to this. So the great beauty about these heat maps is their scalability. Here I'm showing 500 by 1,500 data points. And that works just fine, right? I can see patterns, I can spot where there are high and low values. And so this is really exceptionally scalable. And if I try to show the same data set with a parallel coordinates plot, this is what I would get. And that's not particularly useful, right? You see maybe some kind of like borders between these major clusters, but it's really much less useful overall. Okay, so now I want to do a design critique. And fittingly, because I was talking so much about 3D bar charts, it's going to be about a 3D area chart. Some of you might have seen this. This is from the New York Times again. It's a chart of the yield curve. So the yield curve essentially tells us how much the federal government has to pay to borrow money that's due within certain time frames. So I'll put up this here again because here's the link to the website. If you want, this is useful to play around with on your computer because you need to navigate. But I also have printouts here, and so we'll be handing these out.
Looks like this few areas where the trend actually decreases along the.